Hi guys, we're gonna wait a second to get started. We've got a shorter recitation today, and judging by the number of participants, we'll have a couple more people trickle in. So we'll get started probably in about 2-3 minutes. All right. Can I get someone to let me know that they can see my screen? Anybody?
Yeah, it's there.
Okay, cool. Just double checking before I go off to the races and nobody can see what I'm talking about. How do I get this? Okay. So today's recitation is going to be on the shorter side, largely because we reviewed most of the material that's going to be on your exam when we were doing the exam review last week. Typically, we will do the exam review the day before the exam, meaning we'll have our exams ordinarily on a Wednesday, and we'll do the larger encompassing review that we did last week. We would do that ordinarily today, the day before the exam. I don't know if this is going to be the standard going forward, but what that means for today is that we don't have a ton of material to go over. And so my plan for today, because the main thing that the only thing that Dr. Zalecki emailed me to point out to you guys was a couple of points about the definition of the derivative, which is kind of this crossover subject that is going to bring us into the new unit. And since you guys don't know too much about what a derivative is, unless you've taken courses in the past that gave you a little bit of a leg up in that respect, then we're going to talk a little bit about what a derivative is. So you've got a little bit of background and you're not just doing mindless calculations. Probably do 3 or 4 examples. And then as far as attendance goes, if you are feeling comfortable with the material that was presented last week in recitation, you can feel free to leave. Otherwise, I will hang around and answer questions about the review. If you were a part of the group that was not able to attend the morning recitation last week and you ended up attending my office hours on Thursday evening for credit, you probably got most of what you need out of that because there was more question and answer there. So like I said, if you feel the need to stick around or if you feel like you would benefit from it, please do ask me some questions. But today's recitation is going to be on the short side, and you guys are welcome to go ahead and study whatever you need to do after I deliver this material. So the definition of the derivative, starting with what is a derivative? So the way that we'll see it in English is the rate of change or the slope. The slope is what we're probably most familiar with when you guys were doing algebra, pre-algebra, things like that. The rate of change is also something that's pretty colloquial that we hear a lot, but going forward, these terms will more often than not be used just to bring the idea home of what a derivative is, to reiterate things. The derivative will be referred to as the derivative for this course. So don't expect to see rate of change or slope. You won't often be asked to find the slope. We will refer to it as the derivative. So this is the way that you should be translating it in your brain as you're reading these problems, because like I said, I'm a big advocate for translating math to English before you try and do these problems, because as we go further into this course, the problems will have more and more steps, and you'll really have to understand what's being asked of you in order to navigate those steps. So beyond knowing the derivative and how to translate that in your head, you should also be familiar with this symbolism here. So the d dx that I'm circling over right now, that is not something that I think that we have seen unless you guys have seen it in definition form. And by that I mean they told you that, no, we haven't done that. So I'm not even gonna go into that. But since I was addressing what a derivative was, I thought I'd put it in one place for your studying purposes later down the line if somebody were to look back at this. But what you have seen specifically with the definition of the derivative is f prime of x. So next week and over the course of the next couple of weeks, we will introduce a handful of very sort of integral calculation techniques for when it comes to taking these derivatives. And some of you who have had prior calculus experience, who maybe have taken AB or BC, the AP course in high school, or maybe you guys are retaking this course, you may be familiar with the fact that you have learned that you can take derivatives in a much simpler and streamlined way, but that's what we're going to be introducing to you next week. So the big thing that Dr. Zalecki wanted me to tell you guys is if you are asked to use the definition of the derivative and you use the power rule or any other sort of rule, and if you don't know what the power rule is, that's fine. We haven't taught it to you yet. But if you don't do what's asked of you, you will not receive credit, regardless of whether or not you know a simpler way. You need to do what's asked of you on that particular problem, because that is the concept that is being tested. So coming back to what is a derivative. Looking at this graph, oh, and I should touch on this. This you would say in your head as f prime of x, and I wish I had written that down. But f prime of x is what we are setting equal to the definition of the derivative, and we'll see what that looks like after this page. But when you read this in your head, it should be f prime of x. If f prime of x doesn't hold a lot of information, that's when you go one step forward and you say the first derivative. There are, as we go forward, we will add in an extra comma and it'll be the second derivative. So that just giving you a little bit of background for going forward. But out of all these terms, we're going to focus on this f prime of x term because that's what we set the derivative or the definition of the derivative equal to. So talking about what is a derivative. So if you have not had calculus prerequisites or prerequisite experience in calculus, then look, you should still be able to determine what the slope is of this graph. It's fairly straightforward. So just take a look at it really quick. Think to yourself what you think the derivative might be, and I'm just going to show the answer. And if you think it's obvious, it is. So we get that f of x is equal to 3x. We're able to tell that because of the rise over run, the rate of change. So when we go over 1 in x, we go up 3. So the equation that we are used to seeing, which will also come up in this course, is delta y over delta x. That's rise over run. And that's how we're used to seeing a derivative broken down. But you have been used to seeing derivatives, rates of changes. You've been used to being asked about those from a graphical standpoint. And we will ask you to do that, but not as often in this course. And the big emphasis of the definition of the derivative is that it's a calculation-based method. So what is the derivative of f of x? If I were to ask you what is the derivative, what is the slope of this equation, how much does it change per increment in change of x, the slope would be, 1 second, 3. And so we're able to find this in a more roundabout sort of way by applying the definition of the derivative. And this is not going to be your go-to technique. You're going to want to do, so for something like this, you would use the power rule if you're familiar with that. And going forward on exams, unless you are explicitly told to use the definition of the derivative, we're not going to be upset with you if you do use the definition of the derivative to compute a derivative, unless you are specifically asked to use the power rule, whatever it is. You're not going to lose points unless you don't do what is asked of you in the question. So circling back to the definition of the derivative and how we're going to apply that. So this equation here is something that you should memorize, and it's not too difficult to memorize in my opinion, but I think that the best way to get this sort of cemented in your brain is to, every time that you do a practice problem of this sort, to write out the original equation. Don't just skip straight to plugging in, because that's the first step when we do these, is to plug in based off of the equation that we have, and x plus h wherever there's an x, and then to plug in the equation itself, and we'll see what that looks like in a second. But I did want to make a note about why we're doing this with the h in the first place. So when we do the definition of derivative, if you look up other resources online that differ from the textbook, often the h is delta x. And that makes sense when we think back to this equation up here. We're thinking of it in terms of change in x. So if we look at the limit symbol, we're basically saying as x gets closer and closer and closer to 0, but we're going to represent this change in x as that change in x gets closer and closer to 0, I meant to say, excuse me. We're going to represent it with an h just to keep things, I don't know, that's just the approach of this textbook and of Dr. Zielecki. Other textbooks may do it differently. But what that means is that we're able to cancel out the delta x eventually, and we're able to rationalize, because obviously off the bat, if we were to plug in 0 for every h, we would come up with an irrational term because we would have a 0 in the denominator. In a case like this, can't really use the conjugate. And we'll see that more often than not, we don't really use a whole lot of, so we're used to seeing when you're asked to evaluate a limit statement without the definition of the definition of derivative is not in the conversation, hasn't been mentioned, just what we've been practicing in the past. When you evaluate the definition of the derivative, we have the conjugate and we have algebraic manipulation. You will do algebraic manipulation for these problems, but it's going to be more in line with combining like terms and canceling factors. And not that we don't cancel factors in the other type of problem, but this is less of a factor versus FOIL situation. You just kind of plug and chug and go through the problem. So what we're going to do is every place that we see, so remember we're still working with this equation right here, y equal to 3x. Every place that we see an x, we're going to plug in an x plus h for this first term. So parentheses, always use your parentheses, 3 times x plus h, and then we're going to subtract the original function, 3x over h. And so then as we multiply that out, we get 3x plus 3h minus 3x, and we end up getting rid of the positive and negative 3x terms because they cancel out like we expected. And I kind of skipped and did 2 steps in one here. But once we get rid of these light orange terms, we're left with 3h over h, and we're able to cancel an h from top and bottom, because I'll remind you guys that unless there is an h in every term in the numerator, you're not able to cancel the h, and you haven't done enough work yet. But in this case, 3x is going to be one of the, like, this is a very, if we're able to look at the graph and determine what the derivative of this problem is, that means that it's going to be a fairly simple and straightforward derivative. And so then as we evaluate the limit as h tends to 0 of 3, it's just 3. There's no h in there. Doesn't matter what the delta x is anymore, because so if, for example, if we were looking at a parabola x squared, it would be a little bit more complicated. There would be a variable in there, because as you get closer and as delta x gets closer and closer to 0, it's a curve, so the slope is going to be changing. The slope itself will change, so the rate of change will change. But since this is a uniform linear function, the derivative is the same everywhere, and so we get a constant as our answer. As a reminder, do not use the power rule or any of the other derivative taking techniques if you are asked to use the definition of the derivative. People do lose points on that, and Dr. Zielecki specifically emailed that to me to make sure that I made that perfectly clear to you guys. Okay, so now we're going to do f of x is equal to x cubed. I always write down my equation. For you guys, right now you still have to memorize. For me, it just keeps me on track. So as we plug in an x plus h for that first term, wherever we see an x, there's only one x in this case. So we get x plus h cubed and then minus x cubed. And then we're going to FOIL out. But that should, I don't want to say it should be obvious, but if you see that x cubed there, and you know you have to cancel an h in the denominator, we got to get to that h that's inside those parentheses somehow. And so how are we going to do that? We're going to FOIL and get rid of the parentheses in the cube term altogether and break them down into their individual factors. So I'm going to skip the explanation for this step here. If you guys are struggling with foiling, you can email me or watch Khan Academy video. But we end up being able to cancel a positive and negative term. In this case, it's the x cubed, which is good because then we are left with all terms in the numerator having a factor of h, which means that we can cancel with the denominator. And ultimately, we don't care if there's an h in the numerator, that's fine, because what that means is when we plug in as h tends to 0, it cancels that h term in the numerator. And that is, if that's what the problem calls for, that just helps you get to your answer faster. But so just to, I guess what I'm saying here is, as long as you get the h out of the denominator, it doesn't matter if you have h's left in your numerator in the problem in general, because those it's still rational if the terms cancel. So now moving on, we're able to cancel an h out of the top and bottom. So we still have terms in the numerator that have h's, but like I said, those are just going to end up plugging in as 0. Do not drop your limit symbol until you plug in for 0. That still applies for the definition of the derivative. Whenever you see a limit statement or this limit symbol, you shouldn't be dropping it until you're plugging in the number to which the variable is tending. So cancels those two 0 terms, we get 2x squared plus x squared, which gives us 3x squared. And for those of you who are familiar with the power rule, that tracks. We drop the 3 and reduce the power and then up top, and it becomes 3x squared. Okay. Any questions on the definition of the derivative so far?
I have one question.
Sure.
So what's the difference between f of x plus h minus f of x over h, and then like the f of x minus f of a over x minus a?
They're different forms of the equation.
Okay.
This is the one that I teach. It's the one that I think students get a better grasp of. Every semester, there's someone who will ask that, and this semester I just forgot to even acknowledge it. I usually write them both down. If you opt to use the other one, that's fine. But like I said, some textbooks will put in delta x instead of h. It's a definition, and you would expect them all to be the same, but basically the variables, they're assigned by random convention, right? We make them what they are. And so different textbooks and different resources will present the information to you in different ways.
Okay, so it's just, is this one just like used when you're given like an actual a value in the question? Because like with the f of x plus h one, like you're not necessarily given like an a value.
Yes, so you're always going to use the 0 one, or you're always going to use this form for when your variable is tending to 0. But thus far, I don't know if Dr. Zalecki has given you guys examples of where you tend to a number, has he?
Well, he, like, it was in the notes, but like,
okay,
that's all. So like, would we get points off if we used one or the other, like in a situation?
No. So all I mean is that, so if you use a definition of the derivative, you should be fine. If you get the right answer, you should get full credit. But I will circle back and say that you are able to evaluate. So say they wanted you to evaluate the limit at x, or as, so it's 3 in this case. Say I want the limit at 3. I can evaluate it as h tends to 0, and then I get this equation here, and I'm able to plug in 3 for x squared, because what I have found, when I find f prime of x, I'm finding the derivative of x cubed at any point on the graph. All I have to do is plug in an x value, and I will get the corresponding derivative. Does that make sense?
Yeah, because the this is the method like that I used when I took calc last year. So like, I'm just asking about the
the other options.
Like, because I haven't learned before.
Yeah, you can do, if I don't want to say it as a general rule of thumb, what you did in high school is going to fly in college, but if that's sort of ingrained in your brain and you don't see and you're not given any reason not to use it, then I would absolutely stick to your guns. That's what I do. Clearly, I'm still using the method that I learned.
Okay, thank you.
Any other questions before I move on to the next one?
No, I'm good.
Cool. All right, so now we got one with a fraction. And we got our variable in the denominator just to throw in something spicy for you guys. I don't know. So f prime of x is limit equal to the limit as h tends to 0. We're going to rewrite our equation every single time. So again, so it looks funky to have these fractions, but that's the way that we're going to do it. That you are allowed to divide fractions by other terms. It might be, so there are other ways you can decide to multiply by reciprocals. And you'll see that I maintain this sort of fraction in the numerator situation throughout the problem until I do some canceling. You can multiply by reciprocals and just have two fractions that are just a little bit more complicated if you would prefer. If this whole fraction in the numerator situation is a little perplexing to you, that's fine too. But this is just the way that I chose to do it. So we plug in an x plus h where there is an x for the f of x plus h term, and then we subtract the whole thing. Didn't throw my parentheses in there, but typically when you've got a single term, it is not a big deal. So now I made a note to say that we're going to find a common denominator. Because so this is a type, usually it's just kind of a plug and chug situation for the simpler ones. So for 3x and for x cubed, it's a plug and chug situation, pretty simple. But when we throw in fractions, things tend to get complicated. So, excuse me. What we're going to do is we're going to multiply the top and bottom of this term by x squared, and the top and bottom of this term by x squared plus 2xh plus h squared. And I got that by foiling out the x plus h squared term. So it's going to look something like, oh, awesome. It didn't load. All right. Let's see. This is probably the worst problem to not have had load. But we do have one afterwards. Let's see if it updates. Okay. Thankfully, we don't have too much material to go over today, and so it's not going to be the end of the world if I have to fidget. Here, I'll just write it out, I guess. Okay, so we have got the limit as, okay, which line of math am I on? Okay, so like I said, we're going to have this term and this term, we're going to have a common denominator. So it's going to be, I'm going to skip some of the redundant steps. So I'll just reiterate one more time what I'm doing. In order to get a common denominator for the whole numerator, I mean, I want this denominator and this denominator to be common, disregarding the h in the absolute denominator for now. I'm going to multiply top and bottom by x squared because that's this denominator, and then this whole term here, multiply the 2 and the x squared by that on the right side to get a common denominator. So it's going to end up shaking out to be 2x squared minus 2 times the denominator of the first term I apologize for how slow this is going. And then our denominator is going to be x squared times that same term, the x squared plus 2xh plus h squared. Okay, all over h. So when we start canceling terms, we're going to get, and I don't know that I'm going to rewrite this one, the next line of math, and I'll remind you guys that I send this out to you. I'll send you the recitation note via email, and you'll also get the recitation recording on YouTube as always. But my recitation note will not look like this. It'll be written in a little bit more cohesive. So if I skip steps for the sake of time, just know that it'll be detailed in my lesson note that I send out to you guys later today. So, and going forward, as it pertains to first recitation, I'm going to be sending out the recitation notes and the email regarding this week's or next week's recitation after second recitation. So you can expect to hear from me after 3 p.m. going forward on days of recitation. Okay, so as we FOIL out, we combine like terms in the numerator. It's going to be, and I'm not going to write this one because we're just going to have to do another step of simplification, but this is going to be equal to the limit as h tends to 0 of 2x squared minus 2x squared minus 4xh minus 2h squared over that same denominator that we've been maintaining over x squared times parentheses x squared plus 2xh plus h squared, and then all of that over h. And so if you wrote that down and you're following along with me, we can start to cancel some terms. My finger's cramping doing this. Oh my gosh, I don't know how some professors do this. Okay, so we're going to get negative 4xh plus 2h squared, or is it just 2h? Yep, just 2h. Over that denominator that we keep copying over and over again. And we know what it is at this point. But if you're watching this recording in the future, this little ellipses here is referring to this denominator here. So I don't have to rewrite it for the sake of time. All over h. And so now what we're going to do is we're going to cancel an h from the numerator, not the denominator. That's why I was able to neglect the denominator of this whole fraction and not write in every single term, because what we're going to do first is we're going to cancel an h from the h's in the denominator. And then we'll address well, we won't really have to do much with, I misspoke. We're going to cancel an h from the h's in the numerator that we've just simplified, and then we'll deal with the denominator, but there's not that much to deal with. We'll just end up plugging in. So I'm running out of space. As we cancel an h in the numerator, we just get negative 4x plus 2. Oh, no, I think this is supposed to be 2h squared. Yeah. So that was supposed to be squared, and we'll cancel that. And then we're going to end up with the limit, and that also cancels that in the denominator. So we no longer have an h in the denominator, and we have rationalized. And so if everything's in order, we can just plug in after this simplification step. 4x over x squared times that same denominator. And rather than writing all of this out, well, so it's going to be equal to negative 4x in the numerator. And then when we plug in h into the denominator, every place that there's an h term, it's going to be canceled. Ordinarily, I would type that in as a function. If you're doing a problem like this, this is not a canceling of terms. So you know what? I'm going to take my own advice. If you're doing a problem like this, don't cross out the h and imply that as h tends to 0 for these problems, they end up getting canceled. Write it out as function values, or not function values, as plugged in values. So then we're going to get x squared times x squared plus 2x times 0 plus 0 squared. And then the only two terms that we're left with are these two multiplicative x squared terms. So then we get negative 4x over x to the 4th. Which simplifies to be negative 4 over x cubed. Okay. And that's the answer to this problem. Any questions? Sorry about, thanks for bearing with me on the writing with my finger there. This was the last problem that I did. And so I guess it just didn't have time to upload before I started the screencast. And it looks like once I screencast, the Notability, my app that I use, goes offline. Still working out the kinks as it comes to the logistics of teaching online. Okay, so last problem that we're going to do, we got about 7 minutes. We should be able to crank through it in time. And I'll still hang behind for a few minutes to answer questions if you guys have any, because we will not have any sort of office hours or extra opportunity beyond you sending me emails for you guys to ask questions before the exam. So I will stay behind for a couple minutes. But we have f of x equal to the square root of x. So I wrote down my equation as always. I'm going to plug in an x plus h for the first term, every place I see an x. And I keep saying every place I see an x, even though the examples we've been doing only have a single variable, because you can do this on polynomials that look like 2x squared plus 3x plus 4. Then it's even more important to put your parentheses specifically on this second term here, because then that means that every single term in the original equation needs to be subtracted. So if it's a negative term, it then becomes positive. So it's important to maintain your parentheses in those cases, but there's no extra skills. If you can do what has been presented today, then you just have to do it on multiple terms if you are doing it for maybe a longer polynomial. So we're plugging in x plus h, subtracting the original function. This is an example of one where we're going to use the conjugate. And usually they're pretty straightforward, these ones, but since we've got a square root here and we've got no way to bust that h out in order to interact with it, in order to cancel it with the h from the denominator, then we're going to use then we're going to have to use the conjugate in this case. And thus far, we've been used to seeing the conjugate as being a radical term plus or minus a number, whether it be a fraction or an integer. But here's an example of a radical term and a radical term. It's not going to be too typical that you see these, but square root x is an equation that we love to throw at you in calculus. And so I thought it would be a good one just to have you guys be familiar with if it were to come up on this exam or your final exam. I would expect it to be, it would make more sense to me to see it on your final exam. Again, I'm not going to tell you that it's not going to be on this upcoming exam. But if you can look at this and recognize, okay, I know I've got to cancel the h in the denominator somehow, but there's no way that these two terms in the numerator can interact in such a way that I'm going to get that h out of the radical so that I can cancel it, then I'm going to have to use another tool. And what toolbox do I or what tools do I have in my toolbox as it pertains to limit statements? I got algebra, factoring, foiling, and I've got the conjugate. So we're going to use the conjugate. And I was a little bit redundant with this problem. But so first two terms multiplied are both square roots. And so you're just going to get x plus h for that square root term. The square root of anything times itself is going to be what is underneath the radical. So the square root of 2 times the square root of 2 is going to be equal to 2. Then we get these two terms multiplied. So it's going to end up being negative x. And then, like we always have with the difference of squares, we're going to have the positive and the negative term cancel such that there are only two terms. So we're also going to leave our denominator completely alone. And if you remember from past practice, we do that because, again, we want that h term to cancel. And not that we can't backtrack and factor out the h, or even if you were to FOIL it out on the denominator and just be able to visualize, okay, there's an h for every term in the denominator, so I should be able to cancel it with the h in the numerator. It's still just kind of a waste of time and of energy to write out that extra line of math when you're just going to end up canceling h in the numerator in the and in the denominator. And so I did that same thing I did before, where I kind of did two steps in one, but the two terms in the numerator cancel, so we only have an h left in top, excuse me. So we're able to cancel that h with the denominator, and all we have left is the limit as h tends to 0 of 1 over square root of x plus h plus square root of x, and then we finally drop our limit symbols so that we can plug in 0, and we are left with 1 over 2 times square root of x. And then this would be a perfectly fine answer, this right here. I would not expect you to do this, especially because I've mentioned before that once you've done the calculus, we don't expect you to simplify to any sort of form necessarily. If you've shown to us that you can answer what is being asked of you, we're not going to look for you to drudge up all your old algebra experience. I mean, we will within this course, but if after you finish a problem, if you answer the question as it pertains to the calculus, we're not going to take away points for for simplifying or doing any sort of manipulations after that. What we will do is take away points if you simplify or do manipulations after you find the answer and those manipulations are wrong. But if you left us an unsimplified answer and all of the calculus was correct, you would get full credit. The reason I threw this up here is because as we go into the upcoming unit, we're going to be translating between fractional polynomials and these square roots a lot, because that's the best form as for working through them with the formulas that we're going to be introducing in the coming weeks. So I just threw that up there for just to get it on your radar. And I believe that's the last thing that I have for you guys. Any questions on this problem before I stop the share? No? Okay. Well, at this point, you can feel free to leave if you would like, and I will hang around to answer some questions.
How many questions are on the physical exam tomorrow? Do you know
I do not know, but I can ask Dr. Zalecki for you. I was asked that in office hours, and it's typically not longer than 4 pages. The reason that's not a straightforward answer is because some of the problems are going to be more of a free response situation. And okay, so for example, if you were to do a definition of the derivative problem, it's not impossible that you would get it as a true false, but you would probably just be given space to write out your answer. That might take up a third to a half of your page.
Okay.
But typically on the first page of the exam, I am used to seeing a graph that'll ask you to evaluate the limit as x tends to 2, x tends to -2, or 2 from the left, 2 from the right. One of those problems that we've been practicing so far, where it's like A, B, C, D, E, F, G, but it's technically all one problem. So it's not, I can't tell you there's going to be 15 problems on the exam, because if there's 15, maybe 2 of them would have like 6, 7 other problems embedded in them. But I don't often see exams longer than 3 or 4 pages. And he doesn't overload you guys either. He doesn't try to make it hard for no reason.
Okay, thank you.
Yeah, no problem.
What can we expect, like, of the difficultness of this exam, I guess?
Relative to other exams, it's going to be on the easier side. That being said, some students would disagree with that, simply because going forward, the class is going to be a lot more cumulative. And if you understand the concept of a derivative and what builds from there, you might have a little bit more of a grasp of it. Some students don't really have their brains wrapped around the whole limit situation. So if you're good on limits, then I would say that this is going to be the easier exam of the semester. You're also asking someone who is teaching the course. So relative to other classes that I've taken, I wouldn't say that the exam is hard. But it's not, bottom line, it's not going to be harder than any of the material that we have introduced to you so far. So if you feel even 80% comfortable with, or 80 to 85% comfortable with the material that's been presented to you, there's always stuff that's a little bit harder that Dr. Zalecki will introduce in the semester or before the exam. And then maybe he'll take 1, maybe 2 of those hard examples, and then he'll just kind of keep it at kind of like medium heat so that he can actually test you on these concepts, because he doesn't really want to screw you up. So, and especially since this is the first exam, he will kind of go easy on you guys. It's not going to be easy. It is a college level calculus exam and you should prepare as such, but it's not going to be horrible.
All right, thank you.
Yeah.
I have a question.
Yeah.
So, one of his first lectures, or like his first 2, they were on functions. So I think those are just like introductory types of like lectures, like to get us started on like what kind of functions we're using. But is there specifically anything that we're going to be tested on for the functions section? Or
so you're talking about like the very first lesson, how he had you look at like graphs and prerequisite stuff. Those are kind of like foundational skills, but he's not gonna I would not expect a problem from that assignment or from that practice page to end up on your exam. If you see those concepts, they'll be kind of like in the background. He won't test you directly on them.
Okay. All right, thank you.
Yeah. Any other questions?
Yeah, actually I do. By any chance, could I could you go over a problem in the recitation 2?
Just the one from last week?
Yeah,
Let's
would that
see.
be possible?
Yeah, do you have a specific problem in mind?
Yeah, 31.
Let's do some screen share. $31, you said?
Yeah.
Okay. All right. So this one's honestly pretty difficult for me, at least, to teach. Just simply because it's so abstract and difficult to identify these problems, honestly. But I'll start by addressing sort of like the trick, or it's not, I wouldn't call it a technique because this isn't like putting a positive sign over a positive sign. It's more of like a qualitative evaluation than it is a technique. But basically, with a problem like this, so I will talk about how you would identify it. It's kind of like a process of elimination when you're trying to figure out what technique to use to evaluate these limit statements. And it can be overwhelming. And so I do like to remind everyone that once you get through this unit, it's not going to be like you've got to basically have to have it in your head for this unit, and then it won't come back until the end of the semester. And so you can kind of relax in terms of having those all memorized. But I keep referring to your arsenal, your toolbox. You've got the conjugate and you've got algebra. Those are those two big skills that we use. Looking at this, we only have one radical term in the numerator. We don't have another radical term or a fraction or an integer. So it's not going to be an example of the conjugate. And then we think about algebra. Yeah, we could FOIL out the denominator, but that's not going to do us any good because we're still not going to be able to get that numerator and denominator to interact in such a way that we're going to cancel out that term. And so since we are tending towards a whole, that's what should kind of scream to you. Not all, that's what gave away to me when I was first looking at this, and I still checked the book to make sure that my suspicions were correct. But since we're tending towards a whole, and I know we're tending towards a whole because when we plug in this 9, this is what a whole looks like, is if the factor in the denominator ends up being 0. And since we are tending towards a whole, we're going to evaluate it in this way. Because it doesn't matter what you do to the denominator if you were to expand it, it's not going to help you find your answer. And so the limit as r tends to 9 for r minus 9 to the fourth, and I don't have a graph to show you what this would look like, but it tends towards 0 from the right. And so that's really what it boils down to for determining the denominator. That's the more complicated part in my opinion, because obviously for the numerator, all I did was plug in 9, and all I care about is the sign of the numerator and whether or not it's positive or negative. Then since we've got this behavior down here, whereas r tends towards 9, we have a whole, because if you remember from your pre-algebra experience, when you were asked to graph problems, you were asked to graph asymptotes, and you were asked to graph end behavior, and you were asked to graph wholes also. At least I was in pre-algebra in high school. But this doesn't look like the most obvious whole, but it is a whole, which is what should tell you that the limit as r tends to 9 of that denominator should be evaluated in this sort of incremental way where we want to determine, so we know it's going to tend towards 0. That's obvious to us because when we plug in 9, we're going to get 9 minus 9, which is 0. What we care about is the direction from which it tends towards it. So since it's positive, we say the denominator is positive, and we get infinity. Now, say we had an example where if you plugged in the value, it gave you a positive denominator, but you were tending towards 0 from the left, then it would be positive over negative, and it would be tending towards, or the limit would be negative infinity. Does that make sense?
Yeah, that made a lot more sense. Thank you.
Yeah, good, no problem. Anyone else? See if anybody's still on.
No.
Just
actually,
us?
Yeah, I have another question.
Yeah.
So the true and false, like, is there going to be like a lot of those, or there's probably going to be like just a couple?
I'd say more than a couple. The problem with this semester is that the last 2 semesters, so the second semester that I taught for Dr. Zalecki, I knew exactly what to expect because we had the same time constraints and the class was being taught exactly the same. But now that it's online, and we're going at sort of a different pace, it's possible that he could put less or more of something. If he were to do anything, I would expect less of the true false. But you should expect a handful of those. If I remember correctly, on the last exam, there were somewhere between 6 and 8.
Okay.
But again, that was over a year ago that I looked at that, or not a year ago. It would have been like 6 months or something like that. But you should study those and be familiar with those because you will have that on the exam.
Okay. Thank you.
Yeah, no problem.
All right. Bye. Thank you.
Yeah, good luck.